Hello and welcome back to Calculus 1. This is section 3.1. We are starting chapter 3 on derivatives. So chapters 3 and 4 will be on derivatives, and then later, eventually, chapter 5 on integration. So we start chapter 3 by actually reviewing limits. And technically, the entire lecture today is going to be a repeat of problems that you have seen in 2.3. All of the calculations today are limit calculations. So you should be familiar with this. And this is going to be, obviously, a very good review for the upcoming exam that you all want so much. We start with reviewing few things from algebra, one of which is the slope of the line. Really? Come on. There we go. So slope of the line given as m equals y2 minus y1 over x2 minus x1. So if you have some kind of a line, you are going to have these 2 points, x1, y1, and x2, y2, and you are able to calculate the slope by simply running the formula you are familiar with. Once you have the formula and calculate the slope, you can also calculate the equation of the line by using y equal mx plus b, or y minus y1 is equal to mx minus x1, right? When you use either one of these two formulas to calculate the equation of the line. So this is the prereq knowledge that you need in order to understand what is happening today, and then obviously the basic stuff on how to compute the limit, because that one is because each problem, as I mentioned earlier, is going to be a limit problem today. So let's take a look at the concept of what is called a secant line, which is something that it was there in 2.1, and we skipped 2.1 because this belongs to the whole thing over here, belongs actually in 3.1, where we work out the whole thing. Give me just 1 second. All right, good. So if you have some kind of a function f of x, which is y equals f of x, you can see the x input and the y output right in the notation. And then you can have 2 points somewhere on this curve. The first one, let's say it says x1, and the second one at x2. Now these points would be x2 and f of x2. Those are your x and y. And then x1 and f of x1. So whether you're going to write y1 or f of x1 doesn't matter, right? Well, clearly one is shorter than the other, but it doesn't matter because they mean the same thing. x1 will give rise to y1, and x2 will give rise to y2 once you plug them into y equal f of x. So I can take my good old, before I do that, I have to connect these two formulas with these 2 points with a straight line. That line will have a slope m, and I can calculate that slope m for this line, so we'll call this one m secant. We can calculate m secant by working out on y2, which is f of x2, minus y1, which is f of x1, divided by x2 minus x1. So this formula is absolutely the same as the one we had before for the slope, except this one now is not using, right? It's not using the x's and y's. It uses x's and f of x, which is again the same thing, just different notation. So what we did here is we applied the knowledge, right, from slope of the line and the straight line, and just put it in the framework here where we have some kind of curvy function, and we pick 2 points and draw the line that technically cuts that function. And that's actually what word secant means in Greek language. It means to cut. So that's where the secant came from. So now that we have the algebra prerequisite knowledge and then the pre-calculus upgrade on it, we can finally start talking about calculus situation, which would have a similar picture. We're going to come up with some function, f of x, and then we are going to set a point P. That point P is fixed point, and it has the value of a, and clearly over here f of a as the y value. So that point P is a f of a as its x and y. And then we're going to pick another point and random. That point there is going to be the value x, and that x is going to go to a. Now we already see a particular calculus concept we already learned, because x is going to a. Well, that means that this point, call it Q, is going to P, meaning it is going to, we'll just draw some random locations here. It is going to go through time. You can call this Q1, Q2, Q3, like locations. But there are obviously infinitely many of those. Now what I'm going to do is I'm going to draw all of these secant lines that are going through some of these select Q locations. And each one of those obviously extends right on the other side. They go forever. And if you observe all of these blue secant lines, you can calculate m secant as, now hold on, the point Q I did not write that, so the point Q is x f of x, right? X f of x is for Q, x f of x, and then P is a and f of a. So now, if I want to pick any of the, see, this x is changing, and as that x changes, it drags the other x to change, which changes f of x, which is y. So as the point moves, right, all of these infinitely many points between Q and P will be taken at one point in time by point Q, and that's why we keep it as a variable x and f of x, because that point will literally take on every single position between P and Q. Now, point P is the fixed point, and that one doesn't move, so we're just going to anchor it at a f of a, which is x and y component, right, for the location of the point P. So now if you observe any of the blue lines, right, you will be immediately able to write that m secant is f of x minus f of a over x minus a. So that's just slope of actually each one of the blue lines. So as the blue line moves to any other location than the x at which the line is, right, the second point, that x would be whatever value. You plug that for x and you have a particular slope. Then it moves a little bit, x value changes, and then obviously the slope changes because all of these slopes are different value because the point Q is moving towards P. So we are able to compute all of these slopes, infinitely many slopes. We are able to compute infinitely many of them using just basic algebra. And even if the point Q is to travel past point P, we would still be able to calculate slopes of the line because now, even though Q is on the other side, you still have Q and P to play with. There is this one special location that we actually care about. And that special location is when P collides with Q. So when the 2 points are actually the same point. So we have infinitely many secant lines, but then there is only one red line for P, position P, for point P. There is only one red line. And that red line has a special name. We call that line tangent line. So all of the blue lines are the secant lines, and the red line is the tangent line. So tangent line occurs when Q reaches P and those are in the same location. And hopefully you immediately see what happens without algebra. Right? Can you calculate the slope of tangent line using algebra? What is the problem when point P collides with point Q? There's only one point. But look at the coordinates of those points. What's happening with x values? One x value is a, the other one is x. And when they become the same point, what's the difference between them? Yes. We have 0 on the bottom. Algebra fails immediately. Now we know that the red line exists. We can see it. We know it has a slope because it's a slanted line. You can ski down or hike up the line, right? We can achieve this slope in what you would call the real world because this one is fake over here, right? So we know it exists, but then algebra fails us here and we can't compute it. So what should we do other than panic and be sad, depressed about it? What should we do? What can we do? How do we calculate slope of the tangent line? That is the question. And hopefully staring at this picture, there are there is a clue, obviously, by looking at the picture. But then also there is a sentence which I used earlier a few times that tell us exactly what we have to do. Yes? Well, we don't know what that is yet. The lecture is called Intro to Derivative, but we don't know what the derivative is to deal with that. The only question I have right now, we all know how to compute any of the blue lines. There are infinitely many blue lines in between any points P and Q. P and Q would create a line, and we can find the slope of the blue line by running simple algebra. Right? y2 minus y1, and we're done. And then there are infinitely many Q positions between the original Q and the P. So we can calculate infinitely many of these slopes leading up to point P. So infinitely many of these situations we know. We know also infinitely many after point P, when the Q passes. The only one that we can't use algebra for is when the P and Q are in the same location, and yet that's the only one we care about. So how do we calculate that one? Algebra failed because you told me, we have 0 in denominator, and I agree, because when x finally gets to a, they share the same x value, so if that a is 2, then 2 minus 2 is 0 in denominator, and algebra becomes useless. So what should we do? Yes?
You find the slope of the lines around it. Kind of.
Beautiful. That's exactly what we need to do. But how do we put it together mathematically? What mathematical concept calculates infinitely many locations around the point and doesn't care about the point? Limit. See? So limit is the concept which we studied for the past 2 weeks, where you can calculate infinitely many points before and after the point of interest, never computing at the point of interest. Remember how we had the Romeo and Juliet approach, right? Approach from the left, that means infinitely many calculations coming from left, and then Romeo approach from the right, right? The blue arrow. There was infinitely many calculations approaching from the right. And then what did they used to do? They used to scream the same answer, right? You approach from one side, you get 9. You approach from the other side, you get 9. So the limit is 9. That is the concept that we are going to use now to calculate the slope of the tangent line, the red line. You can calculate infinitely many slopes for the blue lines on either side of P, and you use those slopes to infer, right, to say what the slope of the red line is, because they all go to the same value. Now, to write that mathematically, we simply write that slope of the tangent line is equal to the limit x goes to a of slope of the secant line. So that's mathematical concept. Now, what we do that will be like the theory, right? And what we do in practice here is we say m tangent is the limit as x goes to a of f of x minus f of a divided by x minus a. Now, this form is not particularly useful to us to calculate the slope. So what we do is we go and modify this so it's a little bit more user-friendly as we want to calculate these slopes. By the way, if you are still wondering why are we computing the slopes and why do we care about it at all, well, you should wonder, because I didn't tell you, but slopes measure the change. If you want to see the elevation change, right, for the, let's say, rooftop, or you want to You want to slope your sidewalk a little bit away from the house so that the rainwater is not pouring into foundation, but away from the house. You want to also slope the roads ever so slightly so that the rain is not sticking on the surface, right? So a lot of these slopes, but then also you want to use the slopes to measure how much of an incline you have. As I mentioned, the roofs, okay, and all of these things already, but then maybe there is a steep hill and we need to warn the trucks, right, to use lower gear and a whole bunch of stuff. So there are a lot of applications where you are measuring using the slope, right? You are sloped surfaces, you measure the slope, and very soon we are going to connect that slope and use it to measure change, right? To measure change. So now that we want to measure the change, we were able to calculate all the blue slopes, and then we obviously wanted to know the red one because that was the very special one. So now we want to modify this formula so it's easier for us to compute this slope, and once we do that, we'll be able to do some cool things. Well, let's see. The first all will say, let age be x minus a. So we're going to define a new variable age, and that variable age is going to be x minus a. So now we are going to subtract a on both sides here in the limit. And you can see that on the left side I'm going to get x minus a. On the right side I have a minus a. So this m tangent now is going to be limit age goes to 0. Because you have x minus a, and we said x minus a is age. And then on the other side of the arrow you have a minus a. Well, that's 0. Now, denominator is easy. X minus a we defined as age. So we're good there. And now we have this f of x. We're getting rid of x's, okay? So if I'm getting rid of this x, I'm going to solve this and say that x is equal to a plus age. So instead of having f of x, now I have f of a plus age. And then finally minus f of a. I'm going to leave that as is because it doesn't have x in it. So, right, don't fix it if it's not broken. What does this remind you of? Or should I say, what is this? We talked about it the first day. And then we talked about it when we did 2.3. What is this? Difference quotient, yes. Difference quotient. Good. So now we have the formula here which computes slope of the tangent line. And that tangent line was the red line in our picture, which is the one that went through a single point. And you can see that you pretty much have y minus y divided by 0. You see that? It's cool, right? You have y minus y divided by 0, so it kind of shows that it fits right there to be the formula for the tangent line, for the slope of the tangent line. Again, why? Why are we doing all of this? Well, this formula turns out to be the root of literally everything we know and have. And we'll see how and why. But this formula here computes that you know, what you might perceive of as mundane thing, or who cares. But if just for a second you would consider that everything we have and know, tech-wise, right, economy-wise, and a lot of other ways, due to that formula, I would say it's pretty cool and pretty important thing. So now let's see if we can use this to compute the tangent line. So let's say find the tangent line for f of x equals, let's say, 3x squared minus 6 at x equals to 2. Oh, sorry. Yeah, find the slope of the tangent line. Find the slope of the tangent line. We are going to find the full line later, but we're just going to focus on the slope for 2 seconds. So find the slope of the tangent line for f of x equals 3x squared minus 6 at x equals to 2. So what am I going to do? Well, we'll just crank the formula. You know that the formula is difference quotient. You know that your a is equal to 2. That's spelled out here, right? So a is 2, because the formula is given as x equals a. That's when they meet, right? The point P hits the point Q, so x equals a, which is 2. And we already have what f of x is, so now I just need to figure out what f of a is, which in our case is f of 2, and that's going to be 2 squared minus 6, which is 6, right? 12 minus 6 is 6. And then I need f of a plus h, which is f of 2 plus h. Well, that means that every x gets replaced with 2 plus h. So we have 3, 2 plus h squared minus 6, and we have to work that one out. So now that's going to be what? 3 times, and when you expand this, you square it, you get 4 plus 4h plus h squared minus 6. And then when you work out the algebra, that's going to be 3h squared plus 12h. That's 12 minus 6 plus 6. And now we have all of the ingredients to calculate the slope of the tangent line. Slope of the tangent line was limit h goes to 0 of f of a plus h minus f of a over h. Well, just plug in. M tangent is the limit. H goes to 0. And what do I have? For my f of a plus h, which is this, we have what it is. That's 3h squared plus 12h plus 6. Then we have to go and say minus f of a. Well, minus f of a is just 6. So we have minus 6 divided by h. So just a little bit of chasing around to plug everything where it belongs. And now all we need to do is to do 2.3 limit, right? We learned in 2.3 the way to solve this. So I go and I say limit h goes to 0. These 6's will cancel. Since I can't plug in because I have 0 in denominator, we know that we either have to factor or rationalize or split fractions. Something has to happen. Well, in this case, we can factor out age. Have 3h plus 12 divided by age. And now this age that was bothering us drops. And we just have the limit of, as age goes to 0, of 3h plus 12. And that is 12, because when age goes to 0, 3 times 0 is 0. And the answer is 12. So we calculated the slope of the tangent line to be 12. Sure, now you can go and calculate the rest of the line, but we'll save that for a little bit later. So this particular calculation that you currently see on a screen with the addition of actually creating the difference quotient is in 2.3. You computed the difference quotient and simplifies difference quotient earlier in your life, which is pre-calculus. No one told you probably that it will be used again, and that is going to create something insanely important, pretty much to which we owe all of our technology and a lot more than that. So now let's say that this was happening when x was 2. What if x is 3? Yep, we have to recompute everything. Everything changes if you switch the location for x. So, back to scratch. You know that your f of x is 3x squared minus 6. That's given to us, right? That the text of the problem, 3x squared minus 6. You have to recompute everything. There is nothing you can salvage, because now your f of a, which is now f of 3, is going to be 3 times 3 squared minus 6, and that's 21, right? In the previous problem, you had 6 when it was at 2, and now it's at 3 and it's 21. You have to recompute also the a plus h part, because now it's 3 plus h, not 2 plus h. And that also changes drastically, so you have 3 plus h squared minus 6, and then you have to recompute all of these things. So that's going to be 3, 9 plus 6h plus h squared minus 6. And that is equal to 27 plus 18h plus 3h squared minus 6, for a total of 3h squared plus 18h and then plus 21. And now you have all of the ingredients to run the limit of h goes to 0, f of 3 plus h minus f of 3 divided by h, which now we plug in all of the components we have. So I have f of 3 plus h is 3h squared plus 18h plus 21. And then you have minus f of 3, which is 21, divided by h. These guys cancel, and we get limit, come on, h goes to 0, We can factor out age. We have 3age plus 18 divided by age. So now this age drops. And we have the limit. Age goes to 0 of 3age plus 18, which gives us 18. So slope of the tangent line would be 18. In this case, at x equals 3. Lock the doors. What if x is negative 4? What if x is 10? What if x is negative 1/2? Right? We have to recompute the entire problem every time from scratch. You change location of x, the slope of the red line going through that location is going to change, which is why you have to recompute the whole thing starting from here. Because once you say that you want x is equal to 3, well, then you're calculating f of 3. But if you want negative 4, then you have to compute f of negative 4. And right, that's an issue. So now the question is, can we make this simpler so that we don't have to recompute the whole problem every time we need to figure out the slope? And you might say, well, I don't need to figure out the slope because the world is figured out for me. That's true. But let's say you want one of the high-end jobs. Well, then the line needs to be known. So what do? We take a look at the formula we have to calculate slope of the tangent line as the limit as age goes to 0 of f of a plus age minus f of a divided by age. And we see that we are bothered by constantly changing a, because as soon as you change a, we have to recompute everything. So how about if we fix this formula in such a way that we have to do only one calculation, and then whatever a we get as a value to plug into the answer there? Well, that might be something useful. So we are going to say that the m tangent is equal to the limit age goes to 0 of f of x plus age minus f of x, making sure that this is now the formula that has x rather than specific a. X means all possible values you can think of, right? A is the particular one, which is the reason why you have to recompute everything from scratch. But if I'm able to solve the problem by just computing in general terms, then whatever x is provided to me, I can just plug it in. So let's see. What are the specs? The specs are find m tangent for f of x equals 3x squared minus 6. Note that I did not specify any points. I just said find the slopes. What are you going to find? You are going to find the formula where you can plug in any x and calculate the slope. So what are we going to do now? Well, we already have f of x. We need to create f of x plus age. Now, this is where your pre-calculus techniques and skills should kick in. So when I am modifying x into something else, I need to make sure that every x of the original function is is done with this. So what do we have? We have 3, and instead of x, we have now x plus h squared minus 6. So that's the same equation, except now instead of x, you have x plus h because you are calculating x plus h. If this over here was a heart, then you would have heart squared minus 6. It doesn't matter what goes inside as long as the form of the problem stays the same as the form that you had in original problem. So if you plug in x, it's x squared. If you plug in heart, it's heart squared. And if you plug in x plus h, then it's x plus h squared. So we are replacing now this, and we have to FOIL. So we have 3 times x squared plus 2xh plus h squared, and then minus 6. And now we simplify this into 3x squared plus 6xh plus 3h squared minus 6. And now you have your f of x plus h, which is this mess, and you have your f of x, which is the original problem. Therefore, we can plug everything into the formula and just run through the 2.3 limit, and we're done. So, slope of the tangent line is going to be limit h goes to 0. And now I have my f of x plus h, which is 3x squared plus 6xh plus 3h squared minus 6, minus the original f of x. Well, that's going to be 3x squared minus 6 divided by h. So now you have 3x squared and negative 3x squared, and you have a negative 6 and a positive 6 when that minus distributes. So we canceled a whole bunch of stuff, and now we can just run the limit h goes to 0. Kick out h. We have 6x plus 3h divided by h. Cancel. And we have the limit h goes to 0 of 6x plus 3h. The answer is just 6x. Because when h goes to 0, that doesn't impact x at all. So when h goes to 0, it's 3h that goes to 0, because h went to 0. And what you're left with is 6x. So now, what you have here is that the m tangent is equal to 6x. What were our x's before? Wasn't there x equals to 2? What was the m tangent? It was 12, right? Because 6 times 2 is 12. When our x is 3, what did we have as the answer? 18. Well, 6 times 3 is 18. What are the other x's I asked for? I asked for negative 4. What's the m tangent? Negative 24, thank you. What else did I ask for? I asked for 10 and a negative half. So if x is equal to 10, what's the slope tangent? 60, because 6 times 10 is 60. And finally, I ask for negative 1/2. We get 3. Whew. This function, I gotta write this in blood. This function generates all tangent line slopes. All of them. We do not have to recompute the problem from scratch anymore. All I need to do is to run the calculation once, run it for x. And then when I am done, it will give me the answer in terms of x at the end. And then I keep plugging in the values one by one. I plug in 2, 6 times 2 is 12. I plug in 3, 6 times 3 is 18, and so on. We go through one by one to compute this. So now I have found the fast way. It's not the fastest, but I found the fast way, at least so I don't have to compute each one of these one by one. Now let's see if we can get some emotion out of this. We just found the slope of the line having only 1 point. So far, right, you only knew the formula to calculate the slope of the line. You get 2 points because it was y2 minus y1 over x2 minus x1. Now you get to compute the function, you get to compute the slope, right, having only 1 point. And that point is on the function. And still, who cares, right? Because it's abstract, right? We're calculating some tangent line. No one cares. Until you understand that physics rests on this, and engineering rests on physics, and everything we have rests on that, right? Then it becomes extremely important. Now, Newton didn't exactly do this because at his time, limit did not exist, but he did something close to this. And he's going to stay immortal for all time. Because we understand, right, people that build devices and things in engineering understand the importance and necessity of this. So now, what is this tangent line? The difference between the secant line and tangent line, and bringing it closer to the thing that you see every day, right, as you move about. So what I'm going to do now is I'm going to give you a little graph over here. Going to put again, I'll put the curve like this. And I'm going to pick 2 points, connect them with the blue line, which was our m secant. And then over here on this one, I'm going to draw the red line and put m tangent. And this is going to be our hope of understanding the insane importance of what we just had. What is the difference between these two? The blue line, m secant in blue, if I can erase this, is going to be called the average. And the red one, m tangent, is going to calculate the instant. And those two are two very different concepts. If you are looking at the average, you are looking at the average over the period. And that, looking the average over the period, and that is going to be something that happens over long period of time. So now you are thinking about taking a movie, right? A video with your phone, right? You take the phone, and then first of all you put it like this, and then you record, right? So that later on, when it appears on the internet or somewhere, it's not just a strip like that. So you record a movie, it happens over a long period of time. The red line, see, happens at the single instant, and that's taking a photo. So photograph captures a single moment in time where the video is over the longer period of time. So that's the biggest difference between these two. So you can think of the video versus the photograph. The next one that you can also consider is, I need a volunteer to tell me how far you live from RVCC and how long in minutes it takes you to get here. So how many miles? And how many? 12 miles? And how many minutes it takes you to get here? 30. Excellent. So if you live 12 miles away and you drive 30 minutes, we actually have to use the blue to calculate your, what we call, average speed. So average speed is going to be the distance divided by time, in this case 12 miles, divided by 0.5 hours, if it takes you 30 minutes, is this, which gives us your average speed of 24 miles per hour. 24 miles per hour is average speed. Does this mean that you are always driving exactly 24 miles per hour? No. Because you start with a car being parked. You don't jump into the car that is already moving 24 miles per hour, right? And then over here, getting into the parking lot, you're abandoning the car at 24 miles per hour, ignoring all of the red lights, ignoring all stop signs, ignoring the whole, bunch of cops chasing you because you missed all of the others, right? It's just 24 miles per hour. See, we have the average, and that average happened over 30 minutes, but there are times when you go more than 24, and there are times that you are going less than 24. Like when you're getting into the car. The car is at 0 miles per hour. It's parked, right? So that would be the average. Now, what is the instantaneous? What is that instant speed? Instant speed is every moment of your speedometer. That's the red line. So yes, you are driving down the highway, you happen to look in the rear view mirror, you see the cop car behind you, instantly you are feeling safe and protected, obviously, right? And you just keep driving. What? It's not the case? No. What is the first thing you do? Yeah, you check how fast you're going, right? You see, that instant speed that you have at the moment you were measured is the one you are fined for, okay? If the speed limit is 35 and you are driving 50, you are doomed, all right? You are doomed because you are going 15 over. Now work out percent-wise how much you are going over the speed limit. It's a lot if you are doing 50 on 35. Now, that speed that you see on your speedometer instantly changes when you push one of the two acceleration pedals you have. You have a pedal that is making that speed higher, which is the gas pedal, and you have the other acceleration pedal, which is deceleration, right? It's a negative acceleration, which is brakes, right? Both of those pedals, oh, by the way, if your car has 3 pedals, upgrade, we are in 21st century. So the 2 pedals, right, are both acceleration. One in the positive sense, one in the negative sense. And what it does is make your speed go up or speed go down. What kind of speed? It makes your instantaneous speed, the red line, go up. And that's the one that it's clocked. The other one's clocked too, but more on that in chapter 4. So now, 24 miles per hour is the average speed. And what I know from 24 miles per hour is that you drive through a lot of back roads that probably have a lot of potholes and a lot of stop signs and a lot of traffic lights, and it's, you know, driving through some kind of city and rural, like, there is no highway pretty much at all. Like, maybe you get on like 5 minutes on a highway, but most of the time to have this 24 miles per hour average. So your speed should not be going over 50 pretty much ever in this kind of scenario. 12 miles, 30 minutes. So this is what is calculated by secant, which is the average, which is the original algebra problem. The distance covered, guys, the distance covered is how far you went. So if you are on, let's say, a highway where you have those mile markers, let's say you are on 78, right? And you get on exit, let's go with exit 15. That's Clinton area. And then you are getting off at exit 26, which is where we are right now. The difference between these two exits is 11 miles because the roads are designed to have an exit every mile. If there is nowhere to go, well, they don't put the exit. They just skip it, which is why you have exit 15 and then 17 and then 18, Annandale. And then the next one is, I think, 20 or 20. I think next one is 20. There's no 19. And then after 20, it's 24. There's nothing for 4 miles. And then there's no 25, there's 26. So when you are on 78, well, when you are on any highway anywhere, there should be an exit every mile, but obviously there is no exit if the exit would not go anywhere, right? So you pretty much know when you are on a highway, right? You know which exit you're getting off at. You can always do the subtraction in your head and figure out how many miles you have to go, right? Which in this case, Clinton to where we are at right now is going to be distance of 11 miles. That's pretty much the same. I was about to go with 18 with Annandale, but then I wanted to go closer to your example. Now, when you are on 78, right, and the speed limit is 65 on this stretch, right? If you feel safe, you probably do 60, 65. If you want to feel safer, you go faster so no one hits you from behind, right? Because everyone is driving like crazy on that road. But that's a different talk. That's a different talk. So let's just say, for some reason, right, that the average speed, that the time it's going to take you to go this is 5 minutes to go 11 miles. Lies. 9 minutes. Let's go with 9 minutes. Well, now we can calculate your average speed on the highway. Now, that highway has no traffic lights, has no stop signs, right? And you actually can drive on one speed only. You set on speed, you put the, what is it called? Cruise control, thank you. And just cruise on the same speed through the entire stretch from 15 to 26. say no traffic, okay? I can't say no deer because if you live in New Jersey, you're going to hit the deer. That's 100% guaranteed. How many of you already achieved that goal? 1, 2 only? Really? At least 5 of you are now lying, and you're terrible people for it. Because if you live in New Jersey, at 100% you are going to hit one. Anyway, in your lifetime. But you just started, so hold on. And this is not a prophecy, this is just guarantee. Anyway, so what do we have now? If I want to calculate, again, the average speed, I'm going to take the distance I have to cover, which is 11, and divide that by the 9 minutes, but then we don't like 9 minutes, right? Because we don't calculate the speed in miles per minute. So I have to convert these minutes into hours. So I'll say that 1 hour has 60 minutes, and then these guys will cancel, which would give me miles per hour. So now what I have is 11 divided by 9 divided by 60, and it's going to be miles per hour. So I'm going to get the decimals for this. So let's get the decimals. 11 divided by open parenthesis, 9 divided by 60, close parenthesis. 73.33333333, which is, it's about a ticket, miles per hour. Now, if 73 miles per hour is average and it takes you, you get to the highway at, let's say, 35, 40, to get the highway, then you need to accelerate. And then to get off the highway, right, and maybe you just have to change the lane somewhere, go around the truck or something like that. You are not driving always 73. That means that you have to drive faster than 73 at some point to have the average of 73, right? Because 73 is supposed to be in the middle, and because you had some slowdowns, you have to compensate for the slowdowns with a higher speed to have it at this. So probably you went even up to 80 for whatever amount of time, as little as it needs to be, to kind of make it up for this. Or you just, drove everywhere 75, and then with those slowdowns, getting on and off the highway and so on, it drops it down to 73.33. But again, all of this stuff is average speed. And then you say, yeah, on average I was doing 73, but in reality you were doing 40. When you got on, then you had to accelerate for some time, let's say, depending on what kind of car, horsepower and all that, right? How long will it take you to reach, let's say, 70 or 75, and then drive at that speed, and then maybe change the lane, go around the truck or something, right? That will slow you down. What is the red line? The red line, the tangent line, that is the instantaneous speed. When you read off the speedometer, when you glance on the speedometer. If you touch your either gas or a brake pedal, right, that instantly changes to a different value. So now, what is measured by the velocity? Velocity measures the change in position in respect to time. As the time passes on, your position changes. In order for me to get to that door over there, from the position at which I am right now, time needs to pass so I can get there. So if you say, there is 16 feet between me and the door right now, right? So now I can calculate how fast I am walking by simply computing the average speed. I just need to measure the time it takes me to get to the door. Now that, in today's day and age, right, you can quickly measure by stopwatch, right? So you don't have to go and count Mississippis because it's just not as accurate. So now if I want to go to the door, let's see. This space. 5:25 seconds. 5:25 seconds. So for me to go from desk to the door, we are covering 0 to 16 feet in the distance, so we can call that x equals, and then time start at 0 and ended at 5:25 seconds. And I can now calculate the average speed for me to get to there. Again, that's blue, not a calculus, it's basic one, right? Where we say 16 divided by 5.25. Now 5.25 is going to be around 3. So 16 divided by 5.25 is going to be 3.05, which is going to call it 3 feet per second. That's the walking speed. Did you ever go on treadmill? What are the speeds they have? They have a speed of 3. You're walking 3.5. You're walking. It's 4. It's kind of speed walking. 4.5 speed walking. At 5, depending on the length of your legs, you are either already jogging, right? I can speed walk on 5, but a lot of other people can't. So that depends on the height, right? But at 5.5, I am already running and jogging. I mean, not me, but hypothetically me, right? So, never understood why would anyone go on the treadmill and run. It's like, there's nothing chasing you anymore. So you just go sit indoors. There's no need to run. Have you seen those people run alongside of the road with nothing chasing them? You just want... You kind of want to offer him something like calm down. Once they stopped, say, well, do you need a ride? She ran into the woods. Oh, I drove off. Whatever. Because you want to help people, right? Be nice. So, yeah. Apparently, the treadmill has 10. And 10.5 and 11. Right? So, it's the speed at which you can walk or run. And then there's an incline, right? For some of those, and they go up. And that's going to be the slope, right? Of the incline. And do you think that stuff was just, put together? We're just going to put this together. Everything has to be calculated using this. If you are sitting in this class and you hope to be engineer one day without understanding these concepts, well, I'm sorry. You're going to end up in sales. Because that's what happens to a lot of engineers. They pass their classes, but they still know nothing. And then the company bounces them from one job location, to another job location, to another job location, and eventually they end up in sales. Because it's better to hire an engineer to do the sales, at least they know a little bit about the product, than getting someone who's in a business degree who knows exactly nothing of engineering. Because it's kind of easier to learn a little bit of how to sell than to learn a little bit of how to be engineer. So if you ever hear someone says, oh yeah, engineering, yeah, I have an engineering degree, but I don't use calculus, now you know. Now you know. you have to understand these concepts. These concepts give birth to physics. Physics gives birth to engineering. And then you are able to build things. When you understand the change, the average, the instantaneous, the difference between average and instantaneous, that's what eventually happens. And you are able to understand 3 feet per second and all of these kind of things with the right physics that you eventually take to come up with. So now, what we learned for the 50th time here is that we can calculate the m tangent using the limit h goes to 0 of f of x plus h minus f of x divided by h. Now I get to put this one on a cloud because thank you for all of the tech we have today. That's technically what it is. And now I want to draw your attention to this. We started with f of x is equal to 3x squared minus 6, and we ended up with the m tangent to be 6x. And we said that this one over here generates all tangent line slopes. And those slopes measure instantaneous change. Whether you want to think of the speedometer that instantly changes when you push any of the pedals, or you want to think about photograph versus the video, which is the average. This particular function has a special name. We know that this over here is just function. That's f of x. This one has a special name. The function which generates all of the slopes has a special name, and that special name is the derivative. Yes. So, the derivative of f of x is a function, and we generally call it f prime of x, which generates all slopes for the tangent line. So every single point along the function curve f of x, every single point is going to have a tangent line, and every single one of those will have its own value for the slope. And as you can see, as the line curves, these slopes curve with it. And we are going to, in next lecture 3.2, we're going to see what that gives us. But for now, it's enough for us to know that at any point you draw on the f of x, you can come up with a tangent line, and for that tangent line, we can calculate the slope using the formula we just had. So now, looking at this, right, we would like to know, well, what is a tangent line, right? And the tangent line is the line which measures the change. It measures that instantaneous change, the instant in time. And here are some facts. And all of these can be measured instantaneously as you go about. So here we go. Number one, you are the tallest for the day when you wake up in the morning. Because throughout the day, your body weight will be, because you walk upright, your body weight will slightly compress your joints, and by the end of the day, you will be the shortest for that day. You will go to bed, and while you are unconscious in horizontal position, your joints will expand, right? Everything will relax, and then you will wake up, right? And you will be the tallest for the next day, and then getting every so slightly lower and lower, right? Less tall as you progress through the day. We can't detect those changes, looking just at a person, but you can measure them, and they can be detected by the derivative. The body weight goes the opposite way. You're the lightest in the morning, right? And then, depending on your day, usually the heaviest right before you go to bed. And then there is 6 hours of unconscious state at which your body will be using the energy stored in your body to keep itself running. It takes a lot of calories to run the heart and all other body systems, right? Even if you are a couch potato sitting at the couch all day watching TV and not going out, not doing anything the whole day, you still burn over 1,000 calories just to stay alive. That's it. The body is using a lot, right? And then you add physical exercise, you add going up and down the stairs at your work or school, and maybe you go on biking or something, right? It's going to use more. If you are driving a car, well, your body weight is not changing, right? So it's you sitting in a car. The car is still losing weight. How and why? Fuel, exactly, gas. As you're driving, the fuel is injected into the engine block, exploded, right? And converted into the forward motion through pistons and things, and also converted into heat and noise and exhaust and all of that kind of stuff, which is wasted energy. And at the end of the day, the whole system is losing on its weight because the physical weight of gasoline is converted into all of the other energies that I mentioned. So systems change and evolve in time at all times, and I want to capture the moment in time, and I want to know how much of a change happened in the particular instant. And that would be the derivative. That would be the slope of the tangent line. And you get to define an instant. That instant can be split second, but that instant also could be a whole year in a grand scheme of things. I work on a particular problem in my Calc 2 class. We talk about the population, right? And generally I pick population of humans, right? So if we go and jump real quick into Calc 2 exponential function, exponential model, we can take a look at this population thing. Here we go. So when you take a look at this population, right, you have your good old pre-calculus. This is pre-calculus. You already know this. We expand on it in Calc 2. 2019, you go online, you pick up, there is 7.6 billion people on the planet. You ask Google to tell you how many people were there in 1970, it was 3.7 billion. So in the last 50 years, we doubled the population on the planet. Doubled. Right? Now take all of the deaths that are happening, and you see how much more births we have to double the population. And the death, we have 30 to 35,000 die just in car crashes every year in US alone. 30,000 people, right? That's not natural death. I mean, for some people it's natural, obviously, because drink and drive, obviously. That's called natural selection, right? But, you have everything else on top of this, right? Cancer is another one, right? And we still doubled the population. Then there are wars and homicide and like a whole bunch of other things. So we managed to double the population in 50 years, 49 years. Now look what happens here. We go through all these calculations, come up with blah, 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 blah. And here is the derivative. You remember the f prime? Now we're having a p prime because function for population is p. And we go through calculation, blah, blah, blah. And here is me calculating instant in time, this last line. Calculating instant in time, I want to know how many people we add in 2019. And we are adding 112 million people to the population of the planet just in this year. So these are the things that you can calculate using the derivative. So it's not just engineering. It's going to be economics. It's going to be the policy. It's going to be every single walk of life that you can possibly think of can utilize the measure and calculation of a change. If the system changes, the derivative can see that change, measure that change, and give us the results. So what is the change that I measured in this case of population? I measured that in 2019, the population change happens to the positive side of adding additional 112 million people worldwide. So that's what we are. And when I say instant in time, of course, 2019, that's just 1 year, right? It's the one instant. And pretty much that's all you can achieve also in terms of the birth and death cycle, because it takes about 9 months to cook up a baby. That's going to be only one child per year, because the second child, even if it goes conception right on the date of birth, which is not possible, but let's say, then it's going to be 9 plus 9, 18, that's a year and a half, right? So there can be one birth per, sure, twins and triplets and so on, but there can be one birth, right? One person can be born at a time, and then one death, right, at the time. So it's okay to think of a snapshot in time for population of humans, right, as a year, because you can't really add more than one at a time or remove more than one at a time, right, because you don't get to die twice, right, and you don't get to be born twice either. So it makes sense. So we are adding 112 million people in 2019. Now you can go and you can change to any other year once you have a mathematical model and so on. So this lecture is coming up in Calc 2, but I just wanted to show the derivative. And then, right, you have a whole bunch of other things you can calculate. Over here I also talked about radioactive decay, and we talked about the Advil with the way it, right, comes up in a system. You can do this for any other drug and how it metabolizes and all of these kind of things. So all of these things, right, we can invoke derivatives to give us certain calculus, right, and things. So I just want to do one more example because, again, this section focuses mainly on deriving the derivative formula, which is the one that you already know because you know difference quotient formula. And then obviously the way to calculate, again, that's something you need to know from before because that's 2.3, which is on your exam next class or whatever it is. The only thing you learned today in this lecture is that when you put those old concepts together, you just get to call it derivative. That's it, right? So let's take a look at another. So find the derivative of f of x equals 1 over x. So this is the question. Can I ask this question on the exam? Yeah, but except of using the word derivative, just say find the limit of the difference quotient, right? So if I put the wording find the derivative of a difference quotient, then the what do you call it? The problem becomes 2.3. If I use the word derivative, is 3.1. It's the same question, same mechanics. So what do? We immediately figure out what f of x plus h is. And that is going to be 1 over x plus h. And now we put all of this in the formula and just calculate the derivative. So f prime of x, that's the notation for the derivative, is going to be the limit as h goes to 0 of f of x plus h minus f of x over h. So that's what we have. And now we plug everything in. So limit h goes to 0. F of x plus h is 1 over x plus h minus f of x, which is 1 over x, everything divided by h. So this is, right, 2.3 problem to solve. And we have those tricks up our sleeve. And the tricks are what? Factoring, canceling, rationalizing, adding, subtracting fractions, whatever other thing you can come up with, right? So it's just some of the algebraic tricks. And the one we can use is what? In this case, what is the only thing we can do? Come on. It's obvious, come on. Common denominator, subtract the two fractions. So, multiply this one by x over x, x plus h, and we have the, first off we have this one divided by h, then we have over here x times x plus h as the common denominator, and over here I have x minus h. When I distribute everything, I'm also going to put h over 1, so it's easier to deal with these things. Cancel these x's. Deal with a double fraction where 1 multiplies negative h for negative h in the numerator. And then we have h, x plus h in denominator when the two middle ones multiply into denominator. So whichever way you like to solve double fraction, it doesn't matter. H cancels h. And now we don't have the 0 in denominator anymore. So now when this h goes to 0 because of the limit, we have the answer of negative 1 over x squared. Right? So h canceled h. You're left with negative 1 in the numerator. And over here, since this h goes to 0, this one canceled. You just have x times x. And x times x is x squared. So what we found is that if the function is f of x, and that function is 1 over x, then its derivative would be negative 1 over x squared. So that's what we found. And that f prime will be measuring the change inside the 1 over x. And that takes care of the entire section. Now the next section will tell us the connection between these two graphically, and then eventually we are going to have some of the applied sections where we are actually going to use these derivatives to compute what you call the real world applications, right? Bye.